Okay, so it's fun to be talking at this second annual GGP presentation series and an update for 2021. And this talk is about Canada One Water. It's an integrated groundwater, surface water, climate modeling framework or platform for climate change adaptation for Canada. My co-author, Steve Fry, is at Aquante. And as you might imagine, we're not about to embark on modeling Canada with two people. So there is a long list of collaborators. And firstly, I'd like to acknowledge the pioneering work of Ed Siddiqui, who was at Waterloo and is the founder of Aquante, and Richard Peltier, who's at the University of Toronto and his climate modeling group. Then the cohort of science leads that are in government labs at Aquante and universities. And then the scientific expertise that we're drawing upon to support this endeavor. Funding for this and important acknowledgements required is from the Defence Research Development Canada, DRDC, Agriculture and Agri-Foods Canada, and the Geological Survey of Canada. And then we have a list of partners that are all signatories to the funding agreement within NRCan, Aquante, AAFC, and then the two universities, U of T. Richard Peltier, and at Waterloo, it's Dave Rudolph. So I put together a little abstract here, but I'm not going to read that to you, you can peruse it at some other point if anyone's interested. So the project of objectives, as you might have deduced from the title of the presentation, is to develop a fully integrated groundwater surface water model for Canada. And to use that model to evaluate potential influences of climate change on water resources. So it's fully coupled with historic climate data. The exact time frame is not decided. And then also forward modeling with climate change scenario models. And to translate the eventual model outputs into some kind of societal relevant metrics. And we'll touch on that. We all like to brand ourselves, whether it's with our family name or some other mechanism. In this case, we decided a logo would be appropriate. And I thought I might take a minute to just elucidate the context of the symbolism in the logo and the color. It's fairly colorful and it might leave one wondering, okay, what's going on here? So the yellow and white rays in the upper part of the diagram signify the sun and the solar energy. So a holistic approach to the water cycle is what this project is after, complete modeling of the water cycle. And the energy that drives the system is a key part of that. The rays are also an abstraction of a graduated measure to signify quantification. The centerpiece is a water droplet, stylized as two leaves, or one green conveying land cover and ET, and the pale blue flesh signifying atmospheric water. And then the lower semicircle, which houses Canada One Water, is the dark blue, is signifying groundwater and surface water. And of course, we can even keep going and imagine that the upward form of the water drop just is signifying the return of water through evaporation and ET to the atmosphere. Anyway, there you go. Hope that makes the logo a little bit more understandable. So where does this project come and how does it align with GGP? And we can draw upon the Council of Canadian Academies 2009 Assessment of Sustainable Management of Groundwater in Canada. And that actually was commissioned or co-commissioned by Natural Resources Canada. And they identified a number of significant issues: integrated resource management, the need for climate change scenarios and understanding, some means of addressing decision support, and then an ever-present and important component, communicating results and knowledge to stakeholders and open access to information and data. So we are taking all of those messages from that study and trying to action them in this project. Now, one might imagine or feel that this initiative has kind of come out of nowhere. What is sort of the historic or context for a large national scale regional modeling initiative such as this? And we can delve back into the past to 1969 in a paper by Fries and Harland, which was on fully integrated modeling blueprint. And that set the conceptual framework for the subsequent 50 years of numeric development and in hydrogeological models and progressive movement to large regional models. And the rest of this timeline really focuses more on the development of hydrogeosphere, as René Thirien's PhD work at the University of Waterloo with Ed Siddiqui, and the development of FRAC-3D, and its subsequent application and evolution to 2020, highlighted by the citation in the lower right, by Chen et al., where they produced a national scale proof of concept, fully integrated groundwater surface water model. So that brings us to Canada One Water in 2021. And what's our experience, to delve into this rather awesome or rather challenging exercise? And we've worked with a number of the partners in the project for close to 6 to 7 years now, with Aquante, Canadian Forestry Service, Canadian Geodetic Survey, CCMEO, and the University of Waterloo in different capacities. And a cornerstone of that collaboration and learning exercise was the regional Southern Ontario 3D model and subsequent numeric model that it was developed with Aquante and is published just as an open file at the moment and a data release. And then we have ongoing work with the Survey General Branch, John Crowley, looking at GRACE and how well our modeling results represent GRACE, or how well GRACE is represented in our modeling results, however you want to spin that story. And the Southern Ontario model is being used on a continual basis since its development and release in 2019 by other parties. So its veracity and our confidence in it is maintained by its ongoing applications, and which would hopefully highlight shortcomings that it may have had. So moving from Southern Ontario then and that partnership, we're looking at modeling Canada. And that was the proposal to DRDC for 3 years of funding. And to tackle that problem, it's been decided to parse Canada into 6 large continental scale drainage domains. They are chosen to try and be somewhat equal in size. Only a couple of them are unique watershed in their own right. For example, the Mackenzie River watershed, the Nelson River watershed stretches across the prairies, the Great Lakes St. Lawrence, and then that also includes Atlantic Canada. The others are a multitude of watersheds that all flow into respective oceans. The boundaries are all based on natural physiographic divides or watershed boundaries, and that means the model domain extends into the northern United States and Alaska. In fact, it incorporates nearly 1 million square kilometers of transboundary watershed areas that occur in the United States. Element lengths are going to be between 1 to 5 kilometers, and we hope to discretize vertically the subsurface with 7 or 8 subsurface layers. So the data sets to support this initiative fall into sort of 4 broad categories listed in bold here, and you can see the itemization beneath each one of those. Some data sets are going to be clearly more challenging to develop, but in general, as soon as you start looking at any national coverage for a data set, it becomes a challenge. There are inevitably a myriad of issues that start to emerge. And even with and clearly highlighted in some examples from the GSC or Geomatics Canada for a national DEM to support this kind of initiative. So the modeling framework can be regarded here as three real sort of entities marching across the top of the screen here. From left to right, basically the land surface modeling at 5 kilometers resolution. The central domain is the regional climate modeling using WRF at 12.5 kilometer resolution. And that's interactive with the land surface modeling. And then the groundwater surface water modeling at 1 to 5 kilometers resolution in hydrogeosphere. And so the climate modeling is going to be used, or the land surface modeling, sorry, is using the community land model version 5, and will support both the regional modeling and direct feed input to GW or hydrogeosphere. It's critically important for understanding and modeling permafrost depth and distribution, and to help inform the subsurface parameterization of HGS, particularly with respect to thermal fluxes across that soil freeze thaw and the permafrost melt issues. Then the weather research forecasting or WRF framework will ingest all of the historic climatology information that's being provided by the Canadian Forestry Service and Dan McKinney via or originating to a large extent from Environment Canada, and provide surface energy fluxes for HGS. So that's kind of the framework there. What's our confidence in terms of modeling? How do I change? There we go. So hydrogeosphere, well, let's step back and look at this quote, which is kind of entertaining in this exercise: be realistic and demand the impossible. And you might well say that modeling all of Canada at this scale is impossible. But here we have a model that's stepping through in this animation of the Great Lakes Basin. It's 750,000 square kilometers, 250,000 square kilometers of that is the Great Lakes themselves. And that's nearly half, slightly less than half of our model domains, which fluctuate just around 2 million square kilometers or less. And so through this exercise, we have confidence in being able to scale up to the next order of magnitude in basins. So DRDC is not a science-oriented organization per se. We were funded under the mantra or the of public safety. And that's a significant role for DND in terms of flood events and other natural disasters, forest fires, even COVID. So they want to see some kind of connection with decision makers, community decision makers particularly. And we can break that down into a number of different categories: geographic communities, economic communities. And we anticipate two principal mechanisms for providing information out to those people. One through HGS real-time forecasting platform, which is currently in a proof of concept stage for Southern Ontario and built on top of the Southern Ontario numeric model and hydrostratigraphy. And then also the Groundwater Information Network. So just to show some alignment with GGP in further, Transboundary aquifers are a significant issue between Canada and the United States in some areas. Transboundary watersheds are obviously an even more extensive concern. As we're modeling the natural watershed boundaries, we will include all 61 transboundary watersheds as defined at the fourth order stream level. And that is approximately 2.35 million kilometers square. And it's parsed 45% in Canada, 55% in the United States. And the Great Lakes Basin alone accounts for a large portion of that. And we have a parallel activity to the modeling of actually consolidating information for all of these based on the hydrogeological regions and the conceptualization of aquifers in those regions shown in the lower right graphic. And from a socioeconomic perspective, these transboundary aquifers have a population of 60 million people and quite a range of population stress and economic stress for utilization within these transboundary aquifers or watersheds, sorry. And we're talking watersheds here because we're going for a holistic integrated groundwater surface water modeling approach rather than trying to focus on specific aquifers, which are hard to delineate and characterize. And in that regard, the graphic in the left-hand image in the top right corner of it, highlighting the Milk River, just highlights how, we recognize the limitation of this approach and that aquifers may well extend beyond watershed boundaries. But we have to start somewhere. Validation or matching results, model results with other data sets is going to be a crucial part of demonstrating the veracity of these large regional model. And GRACE is one option in that data set. And just for those not familiar with GRACE, the graph on the right just left, the two pictures on the left just show what GRACE is. It consists of two satellites and it measures mass. You track the change in spacing between the two satellites and its elevation above. And so the left-hand graphic and the right-hand graphic show that, and the change in water level and the amount of snow, which is equivalent water, highlights, and you see the red lines bending closer to the earth as you increase the mass. And you can map down water level changes to millimeter level with GRACE. And there's currently a 15-year record. And John Crowley at the Surveyor General Branch has developed a watershed-based solution for Canada. The drawback to GRACE is its rather large footprint of 100,000 square kilometers. But that being said, the watershed solution really aids in analysis of the data and integration with other data sets. And these two images here just highlight the distribution of changes in total water storage across Canada integrated over 15 years. And the light blue is increasing water and red is decreasing. You see Greenland is in a hell of a hot spot there. But within Canada, you see the Mackenzie Valley red basin in a light pink color. You see the eastern coast of Hudson Bay, James Bay, and Quebec is a much darker blue. So there are both regional trends in Canada. And moving to the right-hand image, you can see the temporal changes that aren't apparent in that integrated signal in the left. So the graph from left to right shows you approximately 15-year time frame, or slightly longer, of increasing water up until 2018. And then in 2019, 2020, somewhat lower storage, water in storage. Now, GRACE only measures total water storage. You have to do additional modeling to separate out groundwater from surface water. And we have an activity in Southern Ontario that's looking at that with integration with the 3D numeric flow model. Communication then. The best project is a failure if no one knows that you actually did any work. So we have a real emphasis on communicating throughout the life of a 3-year project. We initiated it with a flyer and project announcement. The logo and branding is part of that. There's a trilingual website that's available. We're hoping to have a newsletter on an annual trimester cycle, so 3 issues a year, so that we can keep people's attention, but also keep them up to date on what the project is doing, and trying to maintain some social media presence. Then obviously, we think that there's going to be a lot of potential from a science development perspective in this project, so standard sort of peer-to-peer communication. And then GSC data releases. We're hoping that most of the data layers for the modeling will be released through GSC data releases, open files, and an open access data license of the Government of Canada. And one example is the Southern Ontario model. Well, 2 examples, my apologies. And then also the Great Lakes model data set that was developed by Equante, modeling the entire Great Lakes. Engagement, we're continue to work on the Canadian Framework for Collaboration in Groundwater that was developed in 2003 by the program and Alfonso Rivera, through the National Dialogue on Groundwater, which occurs every 3 months as an online forum to communicate with provinces. We're connecting with individual researchers and reaching out to NGOs, conservation authorities. And we're exploring how to actually work with First Nations or engage with First Nations. So in summary, Canada One Water is a relatively ambitious 3-year project. It's fully funded currently. It's highly collaborative across government and the private sector and academia. Its plan is to build a physically based, fully coupled groundwater surface water model that integrates historic climate and has forward modeling climate change scenario capacity. We're hoping to deliver model results through some sort of decision support system, and to support basically, geographic, social, and economic communities dispersed across Canada. And we have an open access perspective, so that hopefully, while the modeling platform will hopefully be sustainable, other people can also take advantage of the data sets that we combine and compile for this initiative. And that's it. Thank you very much. I'll let you read, hopefully at your leisure, the quote from Ed Siddiqui.